So actually, a question I was asked during the lunch break reminded me of something I probably should have said when we were talking about black holes. So I've drawn again the Penrose diagram for the two-sided black hole. And as I explained, if you have an observer, let's call them A and B, one stays on the left, one stays on the right. A massive particle that always stays outside the horizon will end up here, and likewise on this side here. So I've drawn the life history of a massive observer on the left and on the right. They cannot communicate with each other. And their inability to communicate with each other is analogous to the fact that quantum mechanically, if they have access each to their own part of a bipartite state, psi AB, although the state describes a correlation, it's not possible to make use of that correlation to communicate information, because the manipulation of the state by one or the other does not change the density matrix of the other. What I didn't explain, which is a mystery, is which is certainly not understood, what happens to an observer I'll call A prime, who decides that at the risk of life and limb, they're willing to jump behind the horizon. And on the other side, there's a B prime who, likewise, at the risk of life and limb, decides to meet behind the horizon. Well, in fact, they can meet behind the horizon. They won't be able to communicate their findings to the outside world. So the observers A and B who stay outside the horizon will not know what happened. But the classical picture, what's the... The classical picture certainly shows us that the observers A prime and B prime who so choose can jump behind the horizon and meet. And the meaning of that in quantum theory is quite mysterious. That has no analog for an abstract quantum system. So for an abstract quantum system, the two observers who stay outside the horizon can be modeled by observers with access to part A or part B of a bipartite system, psi AB. The observers who jump behind the horizon are obviously, in an essential way, living in the world. They're not just observing it. They've taken things to extremes. They're exploring the black hole, risking life and limb, as I said. And what that means in terms of, let's say, if we did the ADS version of this, where the same thing is true, there's no obvious meaning in the boundary conformal field theory of the observers who choose to jump in and meet. So that's one of the innumerable mysteries in this subject, so I have nothing more to say about it. So I'm going to go back to where we were at the end of the lecture, before lunch, where I proved that if rho and sigma are two density matrices on the same system, then we prove that the relative entropy between them is non-negative, where the relative entropy is defined as trace low log rho minus rho log sigma. So an important special case of that is what's called sub-additivity of entropy. So suppose you have, again, a bipartite system, rho AB, and you have a density matrix that I'll call rho AB. I'm not now assuming that the combined system...
I'd like to change it, because maybe it's the adapter silently dying, or not so silently.
Okay. I'm not now assuming that this combined system AB is in a pure state. We assume that the combined system AB is in a general mixed state described by a density matrix, rho AB.
Okay, it's not the adapter.
Okay. To me, it looks like it works, so I think we should take advantage of that. So we consider a bipartite system AB, but unlike in the past when I generally imagined a pure state on AB, now I assume a general mixed state, rho AB. But I can also then construct density matrix rho A on system A by tracing out HB. And likewise, I can construct a density matrix rho B by tracing out system A. And then I can make a new density matrix, rho A tensor AB. So now I've got two density matrices, which are both density matrices on the combined system AB. Rho AB in general describes correlations between the two systems. Rho A tensor rho B is equivalent if you're only going to measure one system or the other, but it doesn't know about correlations between the two systems. And now we're going to ask what we learned from positivity of relative entropy between rho AB and rho A tensor rho B. Well, this is the trace of rho AB log rho AB minus the trace of rho AB times the log of rho A tensor rho B. But the log of rho A tensor rho B is log rho A tensor 1 on system B, let's say, plus 1 on system A tensored with log rho B. So then this, well, we could say that S of rho AB relative to rho A tensor rho B, continuing from this expression, the first term is minus the von Neumann entropy of rho AB. And the second term is minus the trace of rho AB times log rho A tensor 1 plus 1 tensor log rho B. That's minus what I'll just call SAB. SAB is short for von Neumann entropy of rho AB. And then here, you see, I have the identity on system B. So the only thing that depends on B is rho AB. And I can take the trace over B, which will just give rho A by definition. So this term gives minus the trace of rho A log rho A. And similarly, the last term gives minus the trace of rho B log rho B. So this is SA plus SB minus SAB. And we've learned that that's equal to or greater than 0 because it was a relative entropy. For example, this is used in quantum statistical mechanics to prove that the entropy per spin of a spin system has a thermodynamic limit. A and B could be big blocks of spins, and this would say that the entropy of a block of twice as big is less than twice the entropy of one block. So that would tell you that the entropy per spin goes down as you make the system bigger, but it's bounded below by 0, so it has to have a limit. So that's a common application in rigorous quantum statistical mechanics for a spin system. But instead we'll be using it for gravity. We'll be using it for gravity, except that unfortunately, since this is last lecture, we won't be using it for gravity as much as I'd want it to. You'd find it used more for gravity if you actually look at my lecture notes, the bits we won't get to. But now we're going to discuss a couple of corollaries of this. So we had the system AB, which was possibly not in a pure state. But we know that every quantum system has a purification. So we can assume that there's some C such that the combined system is pure. And for example, rho AB is the trace over the Hilbert space of system C of the pure state density matrix. So in this situation, we prove that SA plus SB is equal to or bigger than SAB. But we could just as well have studied subsystem BC, and the same proof would have showed that SB plus SC is equal to or bigger than SBC. But ABC is pure by hypothesis. So SC is equal to SAB. AB together with C are in a pure state. So SC equals SAB. And by the same logic, SBC is equal to SA. I'm just using the fact that if I'm viewing ABC as a bipartite system where one part is AB, the other part is C. And in a bipartite system in a pure state, the two parts have equal von Neumann entropies. So therefore, SC is SAB, and likewise SBC is SA. So using that, I want to eliminate C from this statement. So SB plus SAB is equal to or bigger than SA. So now I've got two inequalities that only involve A and B. And you see we've proved that SB is equal to or bigger than the absolute value of SA minus SAB. That's called the Araki-Lieb inequality. And similarly, we can prove that SA plus SC is equal to or bigger than SB is equal to or bigger than SA minus SC. So the first inequality says that SA plus SC is equal to or bigger than SAC. That's a statement that this is bigger than this. The second inequality says that SB plus SC is equal to or bigger than SBC. So these two statements, together with this sort of thing, gives us this, which we're going to use in a moment in a more precise discussion of the page curve. Any questions, though, before I do that? So, by the way, I explained subadditivity of entropy, but I'm resisting the temptation to tell you about strong subadditivity, which is important, but we're not going to have time to use it, unfortunately. Although, you can read an example of an application in my lecture notes. Okay, so now we have the page curve. So first I'll describe it the way I did on Tuesday, and then we'll look at it more in the real world. So the ideal case, a black hole is born in a pure state. Then it starts to evaporate. So after a while, we have a black hole plus radiation. The state remains pure, we believe, because it's described by unitary quantum mechanical evolution starting with the pure state. So now we have a bipartite system consisting of the black hole and its radiation overall in a pure state, and therefore we expect that the von Neumann entropy of the black hole equals the von Neumann entropy of the radiation. Now we have a fundamental inequality for the black hole that the von Neumann entropy of the black hole is equal to or less than its thermodynamic entropy. We expect that because it's true for every quantum system. Hawking, on the other hand, maybe I should say Hawking seems to tell us, that the radiation is purely thermal, so that it has the same von Neumann and thermal radiation. That's an oversimplified statement because it ignores the gray body factors. So you have to take gray body factors into account in describing what you mean by the thermal radiation, thermal entropy. But anyway, Hawking seems to tell us that. And therefore, so if we combine this one, which we really believe because of quantum mechanical principles, with this one, which we should be a little bit less sure about, we learned that the von Neumann entropy of the black hole equals the thermodynamic entropy of the radiation. Well, the thermodynamic entropy of the radiation keeps increasing because more and more radiation keeps coming out, always approximately thermal. But as I told you on Tuesday, eventually, as this keeps going up, and if the black hole shrinks so its thermodynamic entropy decreases, eventually this contradicts the fact that the thermodynamic entropy of the von Neumann entropy of the black hole can't exceed the thermodynamic entropy A over 4G. In other words, when A over 4G is less than the thermodynamic entropy of the radiation, they become equal to what's called the page time. And past that time, Hawking's description can no longer be valid. So what's believed to happen, if we plot the von Neumann entropy of the radiation as a function of time, of course that's also equal to the von Neumann entropy of the black hole at all times. It's believed that they increase steadily as predicted by Hawking until we get to the page time, at which there'd be a contradiction, and then they go back down again. The von Neumann entropy of the black hole can't be bigger than its thermodynamic entropy. Its thermodynamic entropy is going down as the black hole shrinks. So its von Neumann entropy can't keep going up. When you reach the point that the von Neumann entropy of the black hole equals its thermodynamic entropy, that means that the black hole is in perfect thermal equilibrium. And it can't be more entropic than that given its mass. Now, what happens beyond that is no longer described by Hawking's calculation, but intuitively, Page gave some more detailed arguments, but intuitively, once a system is in perfect thermal equilibrium, when it is evolving adiabatically by, in this case, emitting Hawking radiation, one would expect it to maintain perfect thermal equilibrium. So once it's true that the upper bound, that the black hole can't have more von Neumann entropy than its thermodynamic entropy, once that's saturated, one expects it to remain saturated for the rest of the evolution. So in this part of the curve, the radiation is purely thermal. In this part of the curve, the black hole is purely thermal. Purely thermal means it has equal von Neumann and thermal entropy. So it's described by an ideal thermal density matrix. So this is Page's picture for the ideal case that the black hole is born in a pure state. Now, I just wanted to have a little bit of fun illustrating things I've told you about von Neumann entropy by considering the more realistic case of a black hole in the real world. So in the real world, we start with a star. It has some thermodynamic entropy. It has some thermodynamic entropy, but more to the point, it has some von Neumann entropy. Now, the star isn't necessarily in a pure state. You might believe the star formed in a pure state, but even if you believe that, By the time it collapses to a black hole, it's been emitting radiation possibly for billions of years. So even if it was initially in a pure state, it's become entangled with its radiation. So you shouldn't assume the star was born in a pure state. Of course, it was born in a state whose when it collapsed to a black hole, it may have had a non-zero von Neumann entropy, but its von Neumann entropy was no bigger than its thermodynamic entropy. Now, like anything else, the star can be purified. So we can say that the star plus C is in a pure state for some C. If you think the star was born in a pure state and that it was in complete isolation in empty space, then C would be the radiation the star emitted in its lifetime before it collapsed. But we don't really need to assume that or know that. Just in general, in quantum mechanics, there can be some state C, some system C, that purifies the density matrix of the star. And you'll see in a moment why it's useful to know that. Then the star collapses to a black hole. And so now the black hole plus C is in a pure state. And the black hole is born in a state whose von Neumann entropy was the von Neumann entropy of the star, because the collapse of the star to a black hole, we believe, was a unitary process described by quantum mechanics, so it didn't change the von Neumann entropy. But this, therefore, is small, because it's much less than the thermodynamic entropy of the black hole. Remember, I told you on Tuesday that for a black hole with the mass of the sun, its thermodynamic entropy, its A over 4G, is 10 to the 20 times what was the entropy of the star before it collapsed. So the von Neumann entropy of the black hole when it's born is no bigger than what had been the von Neumann entropy of the star. So it's no bigger, it's equal to von Neumann entropy of the star, so it's no bigger than the thermodynamic entropy of the star. So at most, it's 10 to the minus 20 times the black hole von Neumann entropy, thermal entropy. So I got tangled, so let me try to say it again. Compared to the thermodynamic entropy of the black hole, the thermodynamic entropy of the star is tiny, 10 to the minus 20 times factor less. The von Neumann entropy of the star can only be less than that, and it's the von Neumann entropy of the black hole at birth. So the black hole is born in a state of tiny von Neumann entropy compared to its thermodynamic entropy. Now, of course, the black hole plus C are in a pure state. Then the black hole evolves. But this is unitary evolution. So after a while, we have the black hole plus radiation, Hawking radiation, plus C. All that's in a pure state. But meanwhile, the von Neumann entropy of C isn't changing because C isn't interacting with the system at all. C might have been beyond Alpha Centauri. So the von Neumann entropy of C is constant. It's also tiny, right? It's much less than the thermodynamic entropy of the black hole. Because the von Neumann entropy of C is the same as the von Neumann entropy of the star before it collapsed. And that's tiny compared to the black hole thermodynamic, compared to A over 4G. So now we have this handy inequality for a three-part system. This one. So let's just remember it. We have SA plus SC equal to or bigger than SB equal to or bigger than SA minus SC, where for B I'll take the black hole, for A I'll take the radiation. And C is C, the system that purified the original star. So in Page's ideal case, the black hole always had the same von Neumann entropy as the radiation. Now, in this more realistic case of the real world, that's not quite true, but the error is bounded by the von Neumann entropy of C, in other words, by the thermodynamic entropy or von Neumann entropy of the star before it collapsed. So in the real world, for a black hole with the mass of the sun, to within an error of 1 part in 10 to the 20, the black hole and the von Neumann entropy, sorry, the black hole and the radiation will have the same von Neumann entropy. So the reason I wanted to explain that was just to help you get a little bit of experience in these basic properties of the von Neumann entropy. Any questions? Yes?
You were saying mostly that the entropy of the star when it collapses to a black hole is the same entropy as the black hole, but the collapse, I would see it as a highly irreversible process. So are you
The
saying
von Neumann entropy is constant in unitary evolution. As I actually explained Tuesday, irreversible processes increase the thermodynamic entropy. They do not increase the von Neumann entropy. The von Neumann entropy, okay. Quantum mechanical, I'll just repeat it though. Quantum mechanical evolution transforms the density matrix by a unitary operator. For example, U is e to the minus IHT for a system with a time-independent Hamiltonian. That doesn't change the von Neumann entropy. So when the star collapses to a black hole, which we believe is described by unitary quantum mechanical evolution, it does not change the von Neumann entropy. It's irreversible because it changes the thermodynamic entropy. Irreversible, all physical processes for an isolated system do not change the von Neumann entropy. They change the thermodynamic entropy if and only if the process is irreversible. We believe the collapse is unitary because we believe that the collapse is described by quantum mechanics, and quantum mechanical evolution is unitary. Okay. The hypothesis that black holes are described by quantum mechanics has been fruitful. It's led to surprising results, but results that hang together consistently. You could also ask me why I believe that general relativity is valid. Quantum mechanics appears to be valid in the real world, and we should assume it's valid in a new situation unless we truly run into a contradiction. The hypothesis that quantum mechanics applies to black holes has led to surprises but not contradictions. Other questions? Yes?
The argument that the thermodynamic entropy of the black hole was much greater than the thermodynamic entropy of the star prior to the collapse.
Well, the thermodynamic entropy of the star is roughly the number of atoms. Take the sun. What is the thermodynamic entropy of the sun? The sun contains 10 to the 57 atoms. And, well, they're mostly ionized, but it contains 10 to the 57 elementary particles in order of magnitude. And the entropy per particle of the sun is not that big. I don't want to say right now if it's 100 or 300 or what, but it's not trillions. So the thermodynamic entropy of the sun is 10 to the 57 times a number which isn't all that big. Then if you have a black hole with the mass of the sun, its thermodynamic entropy is, according to Bekenstein and Hawking, is A over 4g h bar. If you work that out, you'll find out that that's 10 to the 20 roughly times the entropy of the actual sun. So that was the basis. Yes? I can't hear you. If the microphone isn't working, just shout. The question is whether the fact that we observe the black hole affects the entropy. Well, when we observe it, the star had 10 to the 57 atoms. Our observation of the black hole probably involves detecting hundreds or thousands or possibly millions of photons, but not 10 to the 57 of them. So whatever we're doing has a pretty small impact compared to the entropy of the star, let alone the entropy that the black hole is going to have. I see a question in the corner. Shout if you don't have a microphone. If it doesn't work, shout.
Yeah, I was thinking like if we had two stars in the real world, which have similar masses but like kind of different composition, and then we have consecutive, like the corresponding black holes. So like in that case, would the thermodynamic entropy would be the same, like because the stars might have different thermodynamic entropy, but as soon as they become black holes, it would be the same for them. Is it so?
Okay.
Like,
You and your friend each have a cup of tea. From the outside, they look exactly the same. But if you knew, each cup of tea contains an Avogadro's number of atoms. If you knew the atomic microstate, you would say the microstates are quite different. But for practical purposes, they're indistinguishable, and that's why statistical mechanics works. Two stars of the same mass but with different microstates each collapse to a black hole. The microstates are different, but it's virtually impossible to distinguish them from outside, just as it's virtually impossible for you and your friend to determine that your 2 cups of tea are in different states. That's the whole idea of statistical mechanics. And the idea of black hole thermodynamics is that the laws of statistical mechanics apply equally to a black hole, and in particular, the irreversibility we see in black hole physics is like the irreversibility in everyday life. Any more questions? Okay. Guess we'll go on. So I was going to tell you about the Bekenstein bound, which I picked because, well, historically it was the first case. This was understood in about 2006. It was the first case where something really illuminating was said about things related to black holes that required thinking in terms of von Neumann entropy, where an answer was really definitive and people had been baffled beforehand. Now, since then, there have been all kinds of other examples, which regrettably we won't really get to today, probably, but we'll see. Well, we'll see how we do. We might get to do a little bit. But anyway, I do want to tell you about the Bekenstein bound. So, the Bekenstein bound, it goes back to about 1982, which means a decade after Bekenstein's original paper. He revisited the story where he had checked the generalized first law. And as I told you, that check didn't quite work, I would say, because it failed when the photon wavelength was long compared to the size of the black hole. And in hindsight, that could have been a hint of Hawking's discovery that black holes radiate. Anyway, he revisited his story. So he considered a black hole of size, the Schwarzschild radius, which is 2gm. And he assumed it absorbs a body of size r, energy E, and entropy S. Then he wants to know whether the first generalized second law is satisfied in this process. Now, remember that at least for a Schwarzschild black hole, the entropy was 4 pi g m squared. If E is much less than m, then the change in the entropy of the black hole when it absorbs a body of energy E is approximately 8 pi g m times E. And the change in S out is just S of the outside body. I'll just call it S initial, or S of the outside body. Maybe I should just call it S. So we see that the generalized second law is okay if 8 pi gm E is greater than S of the infalling body. E is the energy of the infalling body, and S is the entropy of the infalling body. And 4gm is the diameter of the black hole. It's twice the Schwarzschild radius. So we could describe this by saying that 2 pi times the diameter of the black hole times E is greater than S. If that's true, the generalized second law is okay. Now, if therefore we naively assume and this can certainly be criticized, that the black hole only absorbs a body of size r less than the diameter of the black hole, then you see that if 2 pi Re is bigger than S, then the generalized second law is obeyed in this process. Now, Bekenstein observed that Newton's constant was not in that formula anymore, and that it was just a statement about the system that the black hole is absorbing. So Bekenstein proposed a universal statement in quantum field theory that a localized system of size r, energy E, and entropy S obeys what people called the Bekenstein bound, 2 pi Re bigger than S, or bigger or equal to S. And this statement caused massive confusion over a period of more than 2 decades until it was straightened out by Cassini. In a way, I'll tell you. I was one of the people who didn't take it very seriously for that period. There were, it seems to me, at least 3 obvious objections. I'll label them 0, 1, and 2. So objection 0 was that there's no logic in the proposal because it's just not true. A black hole only absorbs small bodies. So if you have something which is bigger than the black hole, it can't fit into the black hole all at once, but the black hole can perfectly well crush it, and then it falls in. In fact, this happens in the real world. Astronomers observe what are called tidal disruption events, where a whole star falls into a black hole, and it can happen that the star was bigger than the black hole. So the star gets captured by the black hole, it gets mangled, and eventually it falls in. Now, the process in which a star is captured by a black hole obeys the generalized second law. But that's not because the black hole was small enough to satisfy, that's not because the black hole, The natural way to understand the fact that the generalized second law is obeyed when the black hole captures a star is that the star had small entropy to begin with. So this inequality wasn't too hard to satisfy. In fact, the star was big and the entropy is small, so a tidal disruption event in the real world doesn't challenge either the Bekenstein bound or the generalized second law very much. Anyway, the 0th objection is that there's no logic. Now, then what I'll call objection number 1 is that the statement appears to be false as a universal statement about quantum field theory. Now, some people said, well, maybe it's true in the real world, even if it's not a universal statement about quantum field theory. But there was what was for a long time believed to be a trivial argument showing that the Bekenstein bound could not be true as a universal statement in quantum field theory. So, consider a quantum field theory with n free fields, all of mass m. Same mass. And here's a box. And now put one particle in the box, but in a mixed state. So take a state which is the sum of for I equals 1 to n, 1 over the square root of n, with one particle in the box and one particle in some other box. But you've entangled the two boxes, and the system we're going to look at is this box. So, you see, its entropy is sort of log n plus whatever it would be if we hadn't put a particle into the box. And the size and the energy of the box are independent of n, but we can make the entropy as big as we want by making n larger. So based on this, it appears that the Bekenstein bound can't possibly be true as a universal statement about quantum field theory. Any questions on that? Is there a question?
Back here,
Yes?
in the back, over here.
Yes? Go ahead.
So how can they be entangled if they're free fields?
I don't know what to tell you. There's a fallacy in your thinking in asking the question. Entanglement does not depend on interaction. Maybe what you have in mind is how could somebody have created this entangled state if the fields were free? They're nearly free, but they're slightly interacting, and we made use of the weak interaction to create this state. But the weak interaction was much too weak to have any bearing on what we're discussing. That's usually what it means, regardless of what I'm saying now. Normally that's what it means when somebody says, let this be a free field. Nothing is truly free. Free means free enough that its interactions aren't important for what I'm about to tell you. That's general advice. Okay. Sometimes somebody will be literally lecturing on a free field, and then you'll know that that's the case. But when it's a discussion closer to the real world, free means free enough. After all, there's gravity. Gravity interacts with everything. Maybe somebody used gravitational forces to create this state.
So,
Yes?
I have a conceptual question. It may be trivial, but
Yes?
we are defining for a star. We are defining it to have two distinct entropies, a thermodynamic.
That's
And
not
one-
just a star. In general, there are two notions of entropy that I've explained. There's the microscopic von Neumann entropy, and there's thermodynamic entropy. One is constant under unitary evolution. The other obeys the second law.
Yeah, but shouldn't the macroscopic be, in a sense, just a collection of like the subsystem, the quantum system? So can it be, it's like an asymptotic version of it, isn't it? So in a way, a system should be defined in a single entropy. Or
No. I don't think this... I don't want to say more than I have already in trying to describe the two entropies. Thermodynamic entropy is the one that obeys the generalized second law. The second law. And when we talk about irreversible processes or reversible ones, we have in mind thermodynamic entropy as the criterion. Von Neumann entropy is the one we define microscopically. The relation between them is an inequality. Okay. Anyway, this was objection. In my counting of objections to Bekenstein, I've told you objections 0 and 1. So objection 0 was that what was the logic in the proposal? Okay, we can consider the proposal anyway. Objection 1 appears to show that it can't be a universal statement. Maybe it's true in the real world. But objection 2 convinced me that it wasn't an interesting statement about the real world, even if it was true. So if true, is the Bekenstein bound interesting? Or interesting should mean that it's close to being saturated. If it's always off by a huge factor for being saturated, then it's not terribly interesting. So the question really is, okay, a better version of the question is to see is the Bekenstein bound interesting when the terms are well defined? But first, let's just be very naive and try to think of a system we might apply the Bekenstein bound to. Now, Bekenstein, both in 1982 and in his earlier work, By S, he had meant thermodynamic entropy. So we'd better apply the Bekenstein bound to something where thermodynamics makes sense, at least if we think that S is the thermodynamic entropy. We're going to discover that to make sense of the Bekenstein bound, we have to use von Neumann entropy. But in the spirit of Bekenstein's original proposal, let's assume that S is supposed to be thermodynamic entropy. So now we consider a system that where thermodynamics applies. For example, we can have a box with black body radiation. So let the box have a size R and a temperature T. Then, as you know probably from your study of statistical mechanics, S is of order RT cubed, and E is of order R cubed T to the fourth. So Bekenstein says that 2 pi, Bekenstein says that 2 pi RE over S is at least 1. But in fact, 2 pi RE over S is of order RT for a box containing black body radiation. Now we have to discuss for what T does this discussion make sense? We need T much bigger than 1 over R. Well, the wavelength of a photon in this black body radiation is of order 1 over T. And the wavelength had better be much less than the size of the box, or else it doesn't make sense to talk about radiation at temperature T inside this box. So we want 1 over T much less than R. And that means, you see, that the Bekenstein coefficient has to be large to the extent that thermodynamics applies to this situation in a sensible way. The ratio considered by Bekenstein is large, and the lower bound saying it's of order 1 didn't seem terribly interesting to... The lower bound saying it can't be less than 1 didn't seem terribly interesting to me, at least. Now you could ask, why did I consider black body radiation? Why didn't I put a thermal gas in the box? A thermal gas would also be a system thermodynamics applies to. If you put a thermal gas in the box, the bare mass of the atoms is a nuisance. It makes the energy bigger without increasing the entropy. So putting a gas of atoms rather than photons in the box goes in the wrong direction. So how could we improve this situation? Well, we could go to T order 1 over R, and that would make the bound. Then the answer, if I call this thing RE over S, the Bekenstein ratio, if T is of order 1 over R, then the Bekenstein ratio is of order 1. But one thing that goes wrong is that thermodynamics doesn't really apply, so what are we talking about? But another problem is that in this limit, we shouldn't ignore the mass of the box. And the mass of the box is a nuisance. So we'd do better if we get rid of the box. So now we've got no box. And T being of order 1 over R means we just have 1 or a few particles. So our system consists of 1 or a few particles without a box. Well, to me this seems like a reductio ad absurdum. First of all, what's the entropy of a single particle? And secondly, even the size of the state of a single particle is ill-defined in relativistic quantum mechanics. So what are we talking about? So, although I can't really speak for anybody else, to me, well, so even if we ignored objection 0 and 1, objection 2 made me not take the Bekenstein bound very seriously. However, in 2006, Cassini, I think it's 2006, but he was partly building on work of Mayrolf et al. I'm afraid I'm forgetting the other authors' names, although I've got the reference in my lecture notes. Showed that a suitable version of the Bekenstein bound actually is true as a universal result in quantum field theory, despite everything I've told you. So he reasoned as follows. Let omega be the vacuum of a quantum field theory. and let psi be any state in which we wish to test the Bekenstein bound. So he's going to prove a version of the Bekenstein bound, but in the process he's going to reinterpret what the bound means. So as I tried to tell you, the Bekenstein statement wasn't really well defined in the limit where it was interesting. So to prove a universal statement, we're going to have to give precise definitions of what it means. And it won't be exactly what Bekenstein said anymore, but I think you'll probably agree that Cassini proved something that deserves to be called a version of the Bekenstein bound. Then we consider Rindler space. And we're going to live in the right Rindler wedge. And we let sigma be the density matrix of the vacuum for the right Rindler wedge. And we let rho be the same for the state psi. So in other words, we position ourselves in the right Rindler wedge, and we're going to consider the two density matrices that describe all possible observations in the right Rindler wedge, either in the vacuum or in the state psi. And then the fact we're going to use is that the relative entropy is non-negative. Since I wanted to explain the Bekenstein bound is really why I proved this positivity before lunch. And remember, the definition is that the trace of rho log rho minus the trace of rho log sigma. Actually, that's the definition in ordinary quantum mechanics. There's a quantum field theory definition of relative entropy due to Araki, using Tomita-Takasaki theory. It's a rigorous definition of relative entropy in which you can prove the positivity. It's not quite known how to make Cassini's argument in a rigorous fashion using that inequality, although there was a recent interesting paper trying to do that, which I've cited in my lecture notes. I won't try to give the reference now. But anyway, we're going to reason informally as usual. Now, anyway, Araki's story shows that the right-hand side of that relation can be defined rigorously, and generically it's always well-defined, that generically it's finite. It can be plus infinity in some cases, but generically it's finite. But the two terms separately are not well-defined. Now we're going to add and subtract in such a way as to write the answer as a sum of two terms that are well-defined. So I'm going to write this as the trace of rho log rho minus the trace of rho log sigma. Sigma log sigma minus the trace of rho log sigma plus the trace of sigma log sigma. And as you'll see, as you'll more or less see, each of the two terms is separately finite. I won't fully explain that for the first term. Well, what are these two terms? Well, the first term, you can see, is the von Neumann entropy of sigma minus the von Neumann entropy of rho. So we could call it minus delta sigma, minus delta S, where delta S is the von Neumann entropy of the right Rindler wedge for psi minus the same thing in the vacuum state. So delta S is the excess entropy of the state psi relative to the entropy of the vacuum. But this is von Neumann entropy we're talking about, not thermodynamic entropy as originally assumed by Bekenstein in formulating the bounds. Well, so that's what this first term is. It's minus delta S, the difference in von Neumann entropy of the Rindler wedge for the state psi minus the same thing for the vacuum. So naively, if the state psi consists of a single particle a spin half miles away from the boundary of the Rindler wedge, and it's in a maximally mixed state, then delta S is 1. Because the spin half particle in a mixed state would contribute 1 to the entropy, and if it's miles away from the boundary, well, when we subtract the entropy of the one particle state from that of when we subtract the entropy of the vacuum from that of the one particle state, naively we will just get the entropy 1 for the one particle state far away from the boundary. So that's the kind of thing this delta S is. What is the other term? Well, as we learned on Wednesday, if sigma is the density matrix of the right Rindler wedge for the vacuum, if sigma is gotten by taking the vacuum in the right Rindler wedge, then in fact log sigma is minus 2 pi times what I called k right, or minus 2 pi times the integral for, so as before, x is a coordinate which is positive in the right Rindler wedge and negative in the left Rindler wedge. So we learned that sigma, we had a formula for log sigma. Well, I wrote it. In the lecture, I wrote it as a formula for a sigma, which was this. This was one of our main results when we studied Rindler space. So taking the logarithm, we've got this formula for log sigma. Now we have minus trace rho log sigma plus trace sigma log sigma. So that's equal to minus the expectation value in psi of log sigma plus the expectation value in the vacuum of log sigma. I'm using the following fact. The trace of the definition of a density matrix, if rho is the density matrix of a state psi, it means that the trace of rho times any operator, this is any operator in the right Rindler wedge. If O is an operator in the right Rindler wedge, then the trace of rho O is the expectation value of O in the state psi. I'm just using that fact where O is minus log sigma, because log sigma is an example of an operator in the right Rindler wedge. So minus trace, well, this thing can be written like so, but then we have this handy formula for log sigma. So it's 2 pi times the integral, well, so that's the second term in our inequality. Now, when we define quantum field theory, there's some renormalization required for the energy momentum tensor. But this renormalization is only an additive C number. And the additive C number cancels when we take the difference between the expectation value of T00 in the state psi and the same thing in the vacuum state. So that difference is well defined. We usually normalize the stress tensor in such a way that the last term is 0. So I'll do that. But even without that normalization, what we ran into here was well defined. So we have this formula, we have this inequality that 0 was equal to or less than something. And one term in the something was minus delta S, and the other term we just evaluated. So our inequality tells us that 2 pi times the integral over x positive is equal to or bigger than delta S. And this is Cassini's version of the Bekenstein bound. Well, why is it a Bekenstein-like bound? Let me call this thing curly E. So curly E is Cassini's substitute for Bekenstein's E times R. Why is it? Well, suppose we're trying to make this study this inequality. So we take an object and we have an object and we want to see to get a Bekenstein-like bound for that object. So we should put the object in the right Rindler wedge. If we put the object in the left Rindler wedge, then the state containing that object is undistinguishable from the vacuum for measurements in the right Rindler wedge. To make a Bekenstein-like statement, we should put our object in the right Rindler wedge. But we don't want to put it at an unnecessarily large value of x, because that will make the bound less interesting. This will get bigger without changing delta S very much. So we put our object in the right Rindler wedge, but with x being of order the size of the object. And then what we have here is roughly x times the energy density. So this is a quantity that's not exactly energy times size, but it's similar to energy times size for an object that's in the right Rindler wedge, but not at unnecessarily big x. Then on the right-hand side, Bekenstein had in mind thermodynamic entropy, but as I explained, that wasn't going to work in situations where the Bekenstein bound was going to be interesting. Cassini has replaced that with something that's well-defined for all states, namely the von Neumann entropy difference between the state for which you're testing the Bekenstein bound and the vacuum state. So he got a universal inequality where the left-hand side is 2 pi times something which is similar to E times R, and the right-hand side is similar to S. So it wasn't exactly what Bekenstein had in mind, but it's well-defined and it's true for all states in arbitrary quantum field theories. To underscore how much this is true beyond classical intuition, I'd like to say that it's possible for both the left and right-hand sides of this relation to be negative. To Bekenstein, of course, they were supposed to both be positive. You can make quantum states where they're both negative, but nevertheless the proof is valid, so the inequality is satisfied. I'll give you two ways to make I'll give you two ways to make the left-hand side negative, I'll give two ways to get negative things. So first, why can psi kr psi be negative? How can I make a state where that's true? Because naively, kr is an integral of the energy density with a positive weight. Well, let chi be such that kr has a non-zero matrix element between the vacuum and chi. Now, such states exist because kr doesn't annihilate the vacuum. Then let psi be a suitable linear combination of the vacuum and chi. You can pick the coefficients such that psi kr psi is negative. So that's one way to see that the left-hand side of the Cassini version of the Bekenstein bound can be negative, which of course implies that in such a case the right-hand side is also negative. I'll tell you another way to make the right-hand side negative in free field theory. In free field theory, states in the Rindler wedge are entangled with states outside the Rindler wedge. In fact, one of the things we didn't get time for is to do a Sorkin-like calculation of the entanglement entropy, which would have shown it was divergent. So I'd hoped to do such a calculation, but it's one of the things I canceled because it was clear we didn't have time for everything. But anyway, in the vacuum, there is an infinite amount of entanglement between the two sides. Now, if you consider a free field theory, that means there are infinitely many modes on one side entangled with modes on the other side. Now, you could take finitely many states here and disentangle them from their partners on the other side. And that way you could make a state whose entanglement entropy is less than the entanglement entropy of the vacuum. So that's, in free field theory, that's a way to make delta S negative. Anyway, this is what Cassini, how Cassini interpreted and proved the Bekenstein bound. Any questions about it? Yes?
So I have one that I'm trying to reconcile two statements you made.
Yes.
You said that Cassini made a general result for QFT, and then you said that Araki's definition of a relative entry doesn't carry over to this argument. But surely in continuum QFT, I have to use the Araki entropy?
We're physicists. So as physicists, this was a satisfactory argument. But if you're a mathematician and you want to dot the I's and cross the T's, there's something still to do to improve the level of rigor in this argument. This argument is much more precise mathematically than about 99.9% of arguments in physics papers. But there's still a gap, and there's room for somebody to improve it. And there even is a paper I mentioned where people tried to, but I doubt it was the last word.
But you expect that there's not a gap where something interesting happens, it's just a technical gap. That
Well,
would be
the statement that relative entropy is positive is rigorous with Araki's definition. It's the interpretation of that statement that required some physics. But see, the level of precision here is not perfect, but it is much better than more than 99.9% of physics arguments, I would say, comfortably.
May I ask another question?
Yes?
So one criticism of Bekenstein's bound was that it never gets close to being saturated.
This
So
does.
what kind of states saturate
Oh, this can be. Well, as I explained, Bekenstein's bound. So what I really said was that Bekenstein bound isn't close to being saturated in states where his terms make sense. But now that it's a universal bound, it can be close to being saturated. So as I explained, a good case for the Bekenstein bound would be a single particle without a box. The only trouble was that for Bekenstein, that didn't make sense. But for Cassini, it makes sense. Any other questions? So I like this because it was comparatively simple. It didn't take too long to explain. It was historically the first and definitely one of the easiest to explain things where something that was really baffling only makes sense because entropy is understood as von Neumann entropy. There are dozens of things like that that have been discovered since this paper, which was written in 2006. For example, had we but whirled enough in time, I might have told you about Aaron Wall's proof of the generalized second law, which involves the ingredients that went into this proof plus some more. And there are all kinds of other things discovered since then. I've told you repeatedly, but I doubt most of you fully appreciate the extent to which it's true, that we're barely scratching the surface in these 7 lectures. No more questions on the Bekenstein bounds? So I guess I want to tell you a little bit about the following. Why does gravity make entropy finite? When it's divergent in field theory, in ordinary field theory. Ordinary quantum field theory means field theory without gravity. So I'm going to, of course, this is a multifaceted question. There isn't just one answer. I'm going to explain one interesting answer to it. I actually explained a different and more abstract answer the last time I was lecturing in Hamburg a year ago. But here we're going to give one answer. And we're going to do this in the anti-de Sitter space setup. So I guess it's good that I did introduce ADS-CFT duality. So we're going to consider a thermal density matrix in the boundary CFT. Of course, the thermal density matrix has a finite entropy. In the CFT, that's completely clear. The only question is what kind of calculation you have to do in gravity to see that there's a finite entropy. And in the process of answering that, we'll see why a similar calculation without gravity wouldn't have given a finite entropy. So we're going to, well, we don't have to, but we're going to assume beta is small enough that we're in the black hole phase. The only real reason to assume that is that what I'll tell you wouldn't be interesting otherwise. It would be true otherwise, but this is the more interesting regime. So, okay, so to reiterate, so in the boundary CFT, it's obvious the entropy is finite, but we want to do a bulk calculation that will explain the finiteness. And we want to see why a similar bulk calculation would not give a finite answer if there was no gravity in the bulk. So we will, in the process, see the difference between gravity and field theories without gravity. We're going to generalize slightly from the von Neumann entropy. We're going to consider the Rényi entropies. Which I actually introduced before lunch. So we're going to explain a bulk calculation of the Rényi entropies, how it gives a finite entropy with gravity and not a finite entropy without gravity. So we have that picture this morning of the two-sided geometry that goes with the thermal ensemble. And then we describe the density matrix. This row we could think of as the density matrix for the right half of the universe. So the density matrix of the CFT, well, we could take the density matrix of the CFT, but in the duality that corresponds to, in bulk, the density matrix for the right half of the universe. And then, before the break, we discussed how to calculate that. We calculated that we have this picture. There was the two-manifold constructed using R and what I called TE, Euclidean time, and there was a cut from the horizon to infinity. And the boundary values above and below the cut we called phi and phi prime. And rho r as a function of phi and phi prime is given by the path integral in that picture. And as an example of the consequence of that, it follows that there was a factor of 1 over z, right? There was a normalization factor. If we take trace of rho r, to compute the trace, we would erase the cut. And when we erase the cut, we just have a smooth manifold in which we're doing a path integral. And that path integral gives back the factor of z, canceling the 1 over z, so that the trace of rho r is 1. Now, to compute the Rényi entropies, we want to calculate the trace not of rho, but of rho to the alpha, where alpha isn't 1. And we're going to see why that leads to an infinity if the bulk theory doesn't have gravity, and no infinity if the bulk theory does have gravity. Well, how would we construct the trace of rho r to the alpha? Well, rho was 1 over z. Rho r was 1 over z times e to the minus beta times hr. So rho r to the alpha is 1 over z to the alpha times e to the minus alpha beta hr. So e to the minus beta hr rotated the right half of the universe by a 2 pi angle inside the Euclidean Schwarzschild space. Alpha not being 1 means that we're going to rotate by a different angle, namely 2 pi times alpha. So it's a little hard to draw the picture, but the important thing is it produces a conical singularity. Remember, we discovered the Hawking temperature because the Hawking temperature was the unique periodicity such that there was no conical singularity at the origin. Alpha not being 1 now means that we're rotating by the wrong angle. So we've replaced beta by alpha beta, and therefore we're trying to study the system at the wrong value of beta. So now there's a conical singularity at the origin. Well, let me be a little bit more precise about what we're doing. We're going to imagine a theory where the bulk does not contain gravity. So there's no back reaction on the geometry. Then we're taking a rho which was defined by this path integral, and we're going to try to calculate the trace of rho to the alpha for that matter system, a matter system that did not have gravity. Since the matter system that does not have gravity, the geometry isn't dynamical, it's just whatever we choose to study. I've chosen a geometry which determined a rho. And now, for that rho associated with that geometry, I want to calculate trace rho to the alpha. To do that, I take this right half of the initial value surface and I rotate it inside the Euclidean ADS Schwarzschild geometry by the wrong angle. So I produce a geometry that's perfectly fine, except it has a conical singularity. And now we have to calculate the matter path integral in a space-time with a conical singularity. But that produces an infinity. Matter fields interacting. When we renormalized our matter system, we made sure that it would be well-defined in any smooth geometry. We made whatever normalizations were needed to make that happen. But now we're letting it interact with a singular geometry, and it will give a divergence, which you could illustrate with specific calculations. One way to say it is that we're trying to calculate trace e to the minus alpha beta hr, where hr was defined as the operator that moves us forward in imaginary time. And there's no freedom to redefine hr to compensate for this singularity. hr is generating time translations, which tells you its commutators with all the fields on this surface. So the only freedom in hr would be an additive C number, but adding a constant to hr would just be canceled by changing the normalization constant z. So there's no freedom to do anything that would avoid the fact that the trace of e to the minus alpha beta hr will be divergent for an ordinary matter system without gravity if we pick the wrong alpha. The wrong alpha means any alpha except 1. I wish I could make that completely obvious. I'm worried that I'm baffling a significant fraction of the audience, and I can't quite think of what to say. I could call for a question. Maybe a question will show somebody is confused, and then maybe that will give me a thought on what to say. That's one possible solution. Try to ask a question if the question will show that you're confused. Yes.
Hi. Yeah. So before, when we encountered a conical singularity in lecture 3, I think, there was an integral, and this led to a finite contribution. In this case, the conical singularity leads to an infinity. Yes, could you elaborate how exactly this infinity happens?
Well, I'll tell you a fact of life, that if you calculate the determinant of the Laplace operator on this kind of geometry, you get an infinity. That's a fact of life. Does that answer your question? I mean, if I had more time, I would do some kind of calculation for you, but I don't want to do that. This is all that but however, that last statement is the main point. Matter field, if we were to try to calculate, if we take the density matrix, which is defined by this picture, but for a matter system not including gravity, then when we try to calculate its Rényi entropy, we're studying that matter system in a geometry with a conical singularity, and that will produce an infinity. We'll see in a second what happens with gravity instead, but you'll see that with gravity there's no possibility of a divergence. So I have skipped explaining this fact that that determinant is divergent, but I mean, if it was just round, the determinant will depend on the curvature, but if you concentrate the curvature into a delta function, you're going to get a divergence. But anyway, okay. There's probably a little bit more to it than, okay. Okay. I'll say more later if more questions are asked, but I think it's best if we stick with this for the moment. Now let's discuss the case that the bulk system does have gravity. Well, you have to remember the recipe of the ADS-CFT duality. You specify the geometry at infinity and let the system decide what to do. So the system picks its own geometry. So now, if we want to calculate the trace of rho to the alpha, which is up to this normalization constant, the trace of e to the minus alpha beta times HR, that means we take infinity to be a circle of circumference alpha beta rather than alpha times S2. That's a different geometry, but it's a perfectly respectable geometry. At infinity, we just change the radius of the circle. Then we let the theory decide what it wants to do, which means it will pick a classical solution that is asymptotic to this geometry. And at the crude level, which I'm drawing the picture, the classical solution looks the same, except the circumference at infinity is now alpha beta instead of beta. So because the bulk theory had gravity, it can backreact on the geometry. When we change the question, it will change the geometry so as to the geometry remain smooth. And therefore, it will manifestly give a finite answer. On Tuesday, I mentioned that Susskind and Uglum had observed at one loop order a cancellation between the renormalization of Newton's constant and S out. So I've made a statement here that was independent of perturbation theory, but if you expand the statement in perturbation theory in lowest order, it will lead to the observation of Susskind and Uglum. More precisely, if you take alpha to 1 and expand in perturbation theory, you'll get Susskind and Uglum. So on Tuesday night, when I mentioned Susskind and Uglum, I said their arguments have been improved. I've explained one of the improved versions because we didn't have to do anything. I hope you enjoyed that. And maybe I'll stop here for questions. That fact that there was nothing to say to prove finiteness is as close to a joke as we're going to find in black hole thermodynamics, at least at the present understanding. So if I was going to be able to end with something entertaining, that was it. Go ahead. If there's no microphone, just shout.
Okay, so if we start constructing the solution in gravity, perturbatively, I assume to lowest order we'll see this conical singularity, and then there will be corrections that remove this, make the geometry smooth.
Well,
if that is true, what are these corrections?
well, the solution will simply be a black hole with a different temperature, because the boundary condition is appropriate to a black hole with inverse temperature alpha beta. So gravity, when you try to compute the Rayleigh entropy with a given alpha, thinks you're just asking about the thermodynamics when the temperature is 1 over alpha beta. So gravity will do whatever it does at that temperature. So field theory, if you decide to compute the Rayleigh entropy, struggles with the singularity, but gravity has no problem. It just feels that you're asking a perfectly natural question and it answers appropriately. Any more questions? Yes?
I'm still a little bit confused about the conical singularity.
Yes.
I mean, one thing is if you think about the back reaction and gravity making it smooth,
Yes.
it sounds like you look at a stationary point or at something which minimizes
Yes.
reaction. But in general, why shouldn't I, if I think of a path integral, sum over all metrics?
We do. But in leading order in small g, we start with the classical solution, then we expand around it. If the classical solution is smooth, then the perturbation theory is going to be well defined. So because gravity corrected, the field theory, the bulk theory without gravity struggles with the singularity because you asked a bad question. Or what in that theory is a bad question? In gravity, it wasn't a bad question. You just changed the boundary conditions, but gravity will give a sensible answer. If the bulk gravitational theory is well defined, it will give a sensible answer to any such question. If you like, a way of saying what I said without talking about back reaction or anything is just that hypothesis here is that there is an ADS-CFT duality and that specifying any conformal geometry at infinity, gravity will do something and provide an answer. So here, computing the Rayleigh entropy just means changing the conformal geometry at infinity. So if it's true that the ADS-CFT duality works, then the bulk theory will produce an appropriate answer for that question. The story about a smooth geometry is just an attempt to make it a little bit more concrete how that works, at least for small g. Yes?
So what is the point of view, how does the story look from the point of view of confinement? So modifying the temperature on the boundary, for example, if I think about gauge theory is going to produce a confined theory or an unconfined theory, or in the bulk, the black hole state and the thermal EDS transition. But from this point of view, it seems like everything is pretty natural and
well, we didn't learn in detail as a function of alpha what the bulk theory will be. If you ask some alphas, the bulk theory will undergo a phase transition. So you might go past the Hawking-Page transition when you do this. Near alpha equals 1, that won't happen, but if alpha is far enough from 1, interesting things might happen. The only claim here is that while field theory will struggle with the singularity, gravity will just do what it wants to do. Yes, I see another question.
So in terms of the sort of geometrical understanding of this picture,
Yes.
should I think of, so the conical singularity is associated with the horizon of the black hole.
Yes.
So should I think of smoothing out that conical singularity as fuzzing out the location of the
Well,
horizon?
first of all,
or?
the statement that the conical in gravity there was not a conical singularity, right? The whole point of what I just explained was that gravity lets you compute the Rényi entropy without encountering a conical singularity.
Yes, but there's a horizon on the fixed background, and
if you try to compute the Rényi entropy of a black hole without allowing the geometry to fluctuate, you'll think there are divergences. That's quantum field theory without gravity. Gravity does not have those divergences because it avoids the conical singularity.
okay, thank you.
So the first objection to Bekenstein bound that you talked about with n fields, does Cassini's how does Cassini resolve it? Is it by construction?
No,
itself?
very good question, and I thought somebody might have asked. So, gosh. You have to ask, the point is that if you have a very large number of fields, non-classical things can happen. The vacuum has fluctuations where particle-antiparticle pairs will appear. And if n is extremely large, you can't assume that a particle is only in the box if you put it there. It might have fluctuated out of the vacuum. So the probability for mass m for a particle-antiparticle pair separated by r, distance r, is e to the minus mr, roughly. So if there are n species, it's roughly n times e to the minus mr. So when n times e to the minus mr is bigger than 1, classical intuition breaks down. Because you can have a particle well inside the Rindler wedge at a position r, and its antiparticle is outside the Rindler wedge, although you didn't put it there. So the region where the species bound cause trouble is a region where you can't ignore quantum fluctuations. Now, detailed calculations first of all, Cassini's proof was a proof, so it shows there can't be a problem. But Mayrolf and co-authors, and in more detail, somewhat more detail, Cassini, looked at this situation and explained more detail what happens when you try to have many species to violate the Bekenstein bounds. Anyway, it's a good question, and the beginning, at least, of the answer is that, you see, the problem was if log n is extremely big, which means n is exponentially big. And when n is exponentially big, funny things happen that you didn't think about intuitively.
More questions? Actually, I also had a question maybe I can ask.
Go ahead.
When you were deriving the page curve,
Yes.
you said that the von Neumann energy of the radiation was the same as its thermodynamic energy.
Entropy. To the extent that
Entropy, sorry, yes.
Hawking's calculation is correct.
Yes, but you said that this was a statement one could be skeptical about?
Well, you might not trust Hawking. We learned that Hawking's calculation breaks down after the page time. It has to break down after the page time.
Yes.
You might, since not everything is understood about black holes, you might ask me how sure I am that Hawking's calculation is valid until the page time. I'm not totally sure, but I think it's a reasonable guess that Hawking's calculation is valid until it leads to a contradiction. And if you looked at, in his original paper, Page showed that that would be true for reasonably random evolution. And you might think that a black hole is a sufficiently complex system that reasonably random evolution is a good approximation. So, okay.
Thanks. More questions, last chance.
Yeah, so in the first lecture, we saw that Bekenstein thought of the entropy as the number of ways that a black hole could have been
Yes.
created.
Yes.
How does this interpretation fit into the discussion that we have made about the
Well,
von Neumann entropy?
Bekenstein's original proposal isn't exactly what one would say today. A more modern view is that the Bekenstein-Hawking entropy, the exponential of the Bekenstein-Hawking entropy, appears to be the dimension of an effective Hilbert space that is needed to describe the black hole from the point of view of an outside observer. That's the point of view advocated by some modern authors, which appears to fit well what's known today. It might not be the last word.
Thank you.
I see a question here.
No, we've only scratched the surface, but where do you think the field is going?
I don't know where the field is going, but I think the world is in need of some kind of unifying insight about what the relations between gravity and between geometry and quantum mechanics mean. I hope there's such a unifying insight.
Okay, I see no more questions. So in a moment, I will hand over to Volker for some final remarks. But first, let's just take a moment to thank Edward.
But before you do that, I want to say a word, if you don't mind. First, I thank my hosts here in Hamburg for the invitation, and I thank all of you for your patience. But secondly, I just want to remind you that I am leaving you with some homework, because we got through the first 8 sections of my lecture notes at the cost of some skipping. But I'm counting on you when you go home to read section 9 and learn about the Ryu-Takanagi formula. And if you do that, you can then read a very short and fun section 10, which you could regard as yet another joke that's supposed to be at least as fun as that last one I ended with today.
So we've come to an end of this incredible journey that over the last 4.5 days. And as usual, of course, it's a reason to thank a few people. The first one is the helpers in the auditorium. Since it was a random process of finding them, I can't even remember all the names, so thanks a lot. I want to thank Rainer Feller for not only contributing this piece of equipment that I think worked reasonably well. I think we were quite nervous about it. And even to stand here for 12 hours, I think you were sitting there just for the occasional glitches. So thanks a lot for that. Then I wanted to thank Nafise up there. I think early on, sorry. So early on, I think Nafise understood that we really cared about this event very deeply, and she kind of became very passionate about organizing this. And in spite of all the things, all the obstacles that made us, for instance, end up having a colloquium in the university building and things like this, she always found great solutions, and I'm very grateful for your help in these weeks of preparation and also this week. Thanks a lot, Nafise. Maybe you want to come down for a moment? Thank you so much. Okay, but last but certainly not least, of course, I want to thank our lecturer, Edward Witten, for an incredible 3.5 days, very intense days. I remember when we called you to ask whether you would, to convey that the award jury had selected you for the Hamburg Prize for Theoretical Physics. We mentioned that there were strings attached, that you would have to come back eventually and give this course of lectures. You took a few hours, as far as I remember, to think about it, and then came back and says, yes, I'm going to do it. I'm not sure whether you would reconsider this decision after having gone through this week, but I can say for sure, also after talking to many people here, that from our point of view, it was, we're very grateful for this very inspiring 3.5 days, and I'm pretty convinced that many of you will follow your advice and keep reading and going deeper into it. So thanks a lot for all the effort and the patient explanations that you gave to all the questions. Okay, that just leaves me to say goodbye, get home safely, and come back. We have lots of events here at DESY, and maybe another school at some point, going deeper beyond into the surface. Okay, bye-bye.